So firstly, just want to spend some more time because on the homework issue. So some questions which arrived as late as today. I think this still seems to be some confusion around um, what's the right way of handling user input. So firstly, I would like to emphasize that as insofar as the user input is concerned, other than the fact that it's arriving over a serial port from your laptop, this is really no different than handling user input if you were to be writing a C program on your laptop, desktop, or not. It's exactly the same problem. And the thing to remember is scanf is preferred to use because preferable to use because it takes care of all the buffering and all. So like for example, you have a scenario, user types some characters, hits return, types a space, hits return. Okay, so with scanf it will kind of handle all those ugly details of handling those buffers and all, whereas if you are doing getC and all, you have to be prepared for handling unusual kind of inputs in those settings. So scanf is preferred, but scanf is blocking. Okay, so that's the challenge out here. But we talked about uh, concurrency, that how can the system do multiple things so that while one part is waiting for some event to happen, the other part is still doing its job. And one of the concurrency mechanisms that we do have are threads. So you can have one thread which is scanf hung waiting, and other threads are doing other parts of thing like handling PWM generation in software or writing messages and stuff like that. So that's I would recommend should be your first line of attack instead of diving immediately into getC and all that can get pretty hairy. So I've seen from sort of the emails and talks, some people are using getC tied to interrupt handler. Uh, some people are using getS, and some people are using scanf. I think this is hardest. Can be done, but you are essentially implementing what scanf kind of does, except that you have a specialized version of scanf because you know the format. But other than that, but I would almost say that if you're picking that, you probably don't realize what you're getting into, and therefore, precisely for you, it's perhaps the wrong direction to kind of take and think scanf and threads. That's probably the easiest one to go after. Um, uh, I had one student come in yesterday during office hours. I tried his implementation with my little USB uh, monitoring system, and pretty good results. And Adit, could you describe your approach just at a high level for others?
For third question.
For scanf, yeah. For reading the input, like how you did it.
So what I did was in my main loop, I since the user has to enter at any time, so it has to keep running in the background so that when he types, it comes to the foreground. So what I did was just use I found the scanf was blocking, and so once I entered, it was blocking the entire program as such, and so getIS didn't seem to do that. So I got it as a string and then stripped the float and the integer value, and then it seemed to
Okay.
work properly.
So he's using getIS. Um, there might be some corner cases where your approach might fail if the input was coming very rapidly right after getIS and there were some other characters and all, but we're probably not going to check for those cases anyway, so it's fine. getC is really pretty tricky to get it to work. Okay, so and scanf in a thread should work pretty robustly. That's how you would do in a normal if you were to programming. Yeah. So that would be kind of my recommendation. Yeah.
What does it mean when you start scanf in a separate thread, but it still blocks your main thread?
No, it doesn't block your main thread. So it will block the thread in which you called scanf, and then all that will happen is that the scheduler will see that this thread is blocked, and then but some other thread is ready to is runnable, so it will run that.
So is there a reason why your main thread would stop working after
No.
you scanf in a second?
No. If you are calling scanf in a separate thread,
Yeah.
main thread will not support it unless you are doing scanf inside ISR. Okay, because if scanf blocks inside an ISR, then the whole operating system freezes. Okay, so but scanf being called inside a thread which is in parallel to main should not cause any problem. If it is, there's something else kind of amiss there, but it should not. The other thing is I just wanted to rest all of you here in terms of your mind at peace. This is not Mbed is not some boutique OS that I have thrown your way and made you guinea pigs out of it. It's a enterprise quality OS supported by ARM and a whole bunch of companies, and it's been in use. My lab has used it for research for close to a decade. We are among the very first users of this, and we have used it in all sort of production systems and things like that. It works. While it has bugs, no doubt, like any complicated thing, but it certainly are not of the variety where printf doesn't work and all. Okay, so in almost all cases, if printf or these kind of things are not behaving as you expect, there's some other bug elsewhere. Now the problem with embedded systems is that bugs jump boundaries because you do not have memory protection, and therefore they can be kind of a bit tricky to deal with. One of the things you can always do is come to Amro us, because we have access to oscilloscopes and all, so we can at least check which parts of your program are working or not working. Okay, that little thing can just help quite a bit. You're welcome to drop by my office hours. I have this little USB unit I use. It's actually not as precise as what your program will report. Again, when Adit came yesterday, so he gets more accurate numbers from timestamps because the USB unit has kind of somewhat less resolution, but I can provide you some guidance, or you can visit and do it, or go to HKN lab and, or any other lab that you may have access to. Okay. So just wanted to bring mention that. The other thing, let's see what other issues have come up. Yeah, please. Yeah, passing algorithms. Yeah, actually, I tried, and that's not working for me either. Yeah, yeah. So what are you trying to do there actually? So why are you using threads with arguments? So every time user gives a new input, you start a new thread. I think in your case, probably the right way to do is to actually have a shared data structure. So that is one instance where, so you should leave a thread running, which is handling PWM, okay? Except that every time you go through a new period, you should check, you should just lift the new value, okay? So imagine that your period and duty cycle are stored in some variables, and that variable is also visible to the thread which is doing the scanf. Okay, so now you have two threads. One thread is doing scanf, and whenever it parses the scanf successfully, it overwrites those variables. Okay, and then you have another thread which is reached the period in the duty cycle and starts the timers and then works off those. So that way you don't have to start a new thread every time, and then you can keep these things in a. In this case, what Amr had suggested as a global variable is a perfectly fine solution to do. Now, one slight thing that you have to worry about is that because of race condition, you don't want a situation where one cycle, maybe you have a new period and the old, okay, so you can use semaphore or mutex or something like that. Okay, so avoid spawning a new thread every time, because thread spawning itself is costly. Okay. But I will figure out why that, because after I dropped this thing, I tried it myself and yeah, so yeah, that it's not working. So Mbed has bugs. Okay, yeah, so that's the callback approach, and callback doesn't seem to be working. Yeah, but I noticed that they have one other API there which lets you pass a function and arguments, and I'll try that one out. Callback with arguments is not working. Callback is working, but callback with argument is not. So we will be. This is for thread. So thread constructor. passing a callback with argument is not working.
So we wouldn't be marked off for using global variable.
No, we will not mark you. That suggestion was just like something to avoid, because firstly, if I have many threads and I want to, which are all based on the same function, and I want to have them, like for example, let's say I write an LED blinker, and I want to pass the LED ID as an argument, right? So that I have one blinker function, and I spawn thread one with LED1 as argument, another thread with the same function LED blinker but LED2 as argument. Right now we can't do that. So, but in this particular homework you should, and we will not dock points for functionally correct things.
Can you explain really quickly what callback does when you put it in a thread?
Sure. So let me so so this pattern we see in many places in the this operating system, which is I want to create some object and I want to pass to it a pointer to a function as well, so that and we saw an example during last lecture, which was with event and event queues, where events needed a pointer to a function. In case of threads, we're starting a thread and we are telling the thread, this is a function you should run. Okay, so now in previous versions of embed, they basically used to use function pointers. And then at some point in time, they introduced this abstraction called callback, which serves a similar purpose, but is more object oriented, and therefore they started using that. Okay, so callback itself is an object, unlike a function pointer, which is kind of more of a native C class, native C type. So you would see that for threads, for the constructor, they provide several seemingly equivalent versions, right? So I'm in this one, I'm just creating a thread, and we are just giving priorities, stack size, stuff like that. There is actually nothing about pointed out here. So let's see how this one gets used. Okay, so so this is kind of some sort of, you cannot call this function from ISR context, so that's obvious. I can't sort of fire a thread. Initial priority, stack size, name, blah blah blah. Allocate a new thread, but you don't start the execution. So in this case, you will use some other method that the thread class provides to actually then start the thread with the function. So right now, this just creates the thread object. Then the next one uses the callback. Okay. Now, if we look into the callback class, this callback class. So in C++, they have data types which are so-called templated data types. Okay. So the templated data type basically take as an argument of sorts a data type in turn. So this is a class which takes a description of a function and then creates an object there. So let's look at its usage, how it gets used in this particular case. But the main thing is I'm creating a thread where I am passing to it a callback, and rest of the arguments are kind of the same. Okay. So in this particular case, if we look at the callback one, so most of the parameters are the same as before, except that I'm passing the task that this thread should be doing as a callback, so that not only it creates the thread, it also starts it. Okay, let's see. So yeah, here you go. So So this example, unfortunately, doesn't work, but it. So I still have to figure out what's going on out here. So here, when I'm doing a thread start, I'm passing to it callback object. This callback is the small case callback is something that MBAC provides with a convenience variable. This thing takes a function name. So in this case, the function name is length. So that's a function pointer, and then we pass an argument to it, LED1. So this function is written so that it takes as an argument a particular LED and then it blinks that. So I don't have this thing tied together. And this callback blink LED1 is the constructor which creates the callback object, and that's what we are passing. So that's the intent at least, that you are bundling a function pointer together with an argument to that. And this argument is passed by value. So you could have, I don't think it necessarily need a reference out here because this is an int, so that would have passed. So that's how you get to use it, but this example didn't work for me. But if we go back to the man page for the thread, let's see. Yeah, let's look at the callback class actually. Too complicated to explain. Okay. Let's look at more examples out here. So this one, if you noticed, what it is doing is it is so in this case we are passing a different what's happening here? Is it doing the same example? Yeah. So this is the other way to pass things where I'm directly passing the name of the function out here, but in this case I cannot pass arguments to it. So if you, so this does work, but unfortunately it doesn't let you pass arguments to it. So again, if it were to work correctly, then in this type of let's say I wanted a common LED type function and I want to pass it, pass arguments to it, then this will not work. I'll need one separate blinker function for each LED. Whereas callback, were it to work properly, this approach lets you pass an argument. So right now, for purposes of what you were talking about, firstly, you shouldn't have to create a thread every time there's a new user input. I would say just let a persistent thread be running and have a shared object for it. So I'll get back to you on this one, why this is not working. Am I using, are we using the things wrong? I noticed there are some other constructors also out here. I don't know if anyone kind of tried those. So a couple of others. Now, if you were to use this first version, the thread, then you would have to start the thread later on, and at that time you are going to pass the function that you are using to it. Okay, so again, you would see that there are two types of start functions out here. One which is to which you pass standard function, and the other to which you pass a callback. So there are two variants, and I think somewhere along the line they kind of did a transition. Other thread-related functions you would see, which are kind of useful for us. You can change priority. By default, it's all threads start out at some default priority. Okay, and then you can manipulate the stack and stuff like that. You can even pass ID of a thread from one thread to another, so you can use them for message communication and stuff like that. So there are a whole bunch of other stuff out there, but again, in this assignment, you didn't need any of those. Okay. Any other questions? Okay, so last time we kind of started looking at wireless, and I talked a little bit about at a very superficial level as to what. Well,
Actually, before we move on from the programming and embedded systems, why do we use static variables so much rather than writing classes and being more careful with the main thing? It's a really broad question.
well, I mean, firstly, there are two orthogonal things, right? I mean, there's classes are just data types,
Yeah.
and you can have a static instance of a, right? Okay.
Right.
Now, the reason in embedded systems, so firstly, generally static variables are frowned upon, which is why my response to response, which is from a purely software engineering perspective, static variables are kind of evil because they basically can have spillover effects, right? As in our example. But in embedded systems, static variables do have one advantage, which is they can let you estimate how much data memory is going to be needed. So if you think about you're operating in a system where everything is in a single address space, so stack, heap, which is where your dynamically allocated memory when you allocate a new object goes, and the static variables, they're all residing in a shared address space, whereas on normal in sort of normal programming, you can put them into separate so-called segments, separate pages, and you can kind of have them far enough apart. But here we are memory constrained, your stack spills over, and as it grows, I have no idea how much memory it's going to take because oftentimes you have loops and stuff like that. So trying to put your data into static means that I can estimate how much memory it's going to take. And in fact, I don't know if you guys notice on Mbed online compiler, to the right hand side, it actually shows you after you compile the program what is the size of the program memory, what's the size of the thing. But one thing it cannot tell you is the size of the stack. So from that perspective, it is better to keep things static as opposed to creating them as local variables, particularly if you have large objects. So that's one reason, being able to estimate before you start to run how much memory you're going to need, and that is important in static embedded systems. Okay. In fact, there are certain embedded systems where, as an architectural reason, they do not allow for any form of dynamic object creation. The only you do need the stack. There is no escaping from that, but there's no heap, just so that you move away from both kind of the overhead of dynamic memory allocation as well as the uncertainty which arrives in terms of memory usage there. Okay. One other sort of side comment I would make is that being able to estimate at compile time whether you will run out of memory or not, these kind of statements is pretty important. And there are newer programming languages which seek to provide some assurance. There is a new programming language which embedded system people are getting very interested by. Is a language called Rust. Let me see if I can pull that up. So this programming language, the Rust programming language, and the main thing is, as you see, it says that runs pleasantly fast, so it's kind of like C, C++, but prevents segment faults. It basically means kind of spilling over out of your part of the memory space, guarantees thread safety and stuff like that. So it's a language designed specifically so that at compile time, compiler can do a lot of checks about the safety and security, actually, it turns out, of your program. So at some stage, given the prevalence of bugs and all, and this is something even general purpose computing systems face and exploit, but embedded systems particularly, so Rust is becoming quite, it's getting increasingly popular for that purpose. So just something we're looking at. Yeah.
Yeah, I'm surprised that, or how come embedded systems aren't moving to this more quickly? Because C++ has horrible runtime
So the C, the thing is the
Right,
performance
yes.
gap. Okay, so I don't know if some of you noticed, but for Hexaware, if you go to the website, somewhere they have a link saying you can run Python on Hexaware. Okay, so you have sort of a language which is something like 20x slower than C or C++, being run on Hexaware, and it takes a lot more memory. Um, Not really viable. I mean, yeah. So I think it would be languages like Rust which will eventually kind of come in the way. But right now, they're too booty. Part of the problem is also there's no support in terms of debugging and all. So yes, but there is a operating system called Tock, T-O-C-K, out of Stanford, Berkeley, which is runs on Cortex M and all. The problem is it misses most of the interesting device drivers and all. So until such time they emerge, it will remain a bit of a boutique thing. Okay, any other programming questions? I also wanted to comment on kind of the homework late day policy and stuff like that. So uh, we have total of 4 late days. You are expected to keep track of them. So um, on Gradescope, I allow for late days, and the system will perfectly happily let you make use of more late days than you are allowed over the course of the quarter, and then we will just deduct points at the end. So very important that you don't exceed 4 late days. Okay. Uh, Pardon me? No, because your submission time is recorded. Okay. One very important thing is the following. So what Gradescope allows you to do is, let's say you submit a revised thing, okay? But you can always select which submission you want to be considered, okay? And that's what gets counted. So let's say, for example, you submitted a submission before the proper deadline, early deadline. Then you submitted another one after the fact, but then you change your mind that, hey, I don't want to use the late day. Then you can go back and before we start grading, as long as you select the one which you submitted earlier, then it doesn't get counted. Okay? So the system allows you to do that. What it doesn't do is keep track of your late days because it doesn't know that there is a total quota of 4 late days. Okay, so just keep that in mind. So the other thing was originally I announced no late day for this particular assignment and that a cap of 2 late days. But then I got request we need late days and all. So I'm not going to enforce any of that. You just have total of 4 late days for the quarter. Use whichever way you want. You want to use all 4 in this assignment, be my guest, but it's probably not very wise. The other thing is, I originally said there will be one programming assignment, this one, followed by 3 more, but I think because of the pace which we've progressed, we will only have 2 more programming assignments. So just want to let you know of that. We'll keep all of them even, basically. Okay, so 3 programming, total of 3 programming assignments. So this one, 2 more. Okay. So let's move on so that I can at least, I know there's only 10 more minutes remaining. So medium access control and sharing the wireless link. So we talked about topology. The other issue which comes up in wireless is that you have a shared link and every radio is trying to transmit on them. And their packets are going to trash each other. So the main issue in this thing is that if I'm a receiver and if I can hear 2 transmitters, then if they transmit at the same time, then I would have a hard time disambiguating the 2. And while there are some new techniques emerging which can help me separate out, but generally I can't. So the goal is that no receiver should be in a position where it is hearing 2 transmitters transmitting at the same time. It's certainly fine that one transmitter near me is transmitting, another transmitter far away is transmitting, but I cannot, it's too far away to influence me. So you can still have multiple transmissions taking place in space. The only thing you want to prevent is that 2 transmissions don't take place so that a particular receiver can hear them. So we face the same issue in wires also, no different. Ethernet also has the same issue. And so the part of the system which controls this thing is called MAC, which stands for Medium Access Control. Okay. My Apple Pencil came up. MAC controls when and how each node can transmit in the channel, and so things there are many. So the main thing is the following: somehow we need to separate out these transmissions. So I already talked about that we can separate them out in space. So that certainly is one way, namely don't transmit near me. So we can have I transmit to him, and then two people at the back can transmit, and if we are too far away, we are fine. But other ways of separating things out, we can separate out in frequency. So I can transmit in one frequency, and someone nearby can transmit in a different frequency. There is also a notion of using some sort of a code, which is if you go into your linear algebra, you can think of like I can take a coordinate system and I can have other coordinate systems which are kind of rotated versions of them and all. So there's a concept where I can kind of project things into a different space, so to say, and do it. So it's called spread spectrum. Okay, there are many ways of doing it. You'll encounter in some contours. But the most important one is we separate out in time. That is, we are operating in the same frequency, same code nearby, and we are going to have some sort of an arbitration protocol so that two radios don't collide. So that's the most important part, collision avoidance. But additionally, there are other objectives that we have. Energy efficiency, as in radios take energy to receive, transmit, etc. So you want the whole process to be energy efficient, and particularly for embedded devices that matters. They should scale so that this should have been a separate bullet latency. You want to also make sure that communication latency is met. It should be fair. So it should not be the case that one radio gets to hog the shared medium. We should all get sort of equal, somewhat fair chance. Overall throughput should be good. I can be fair, but could be kind of socialistic, as in no one gets anything, so everyone gets zero. That's not good. So you want to also maximize the overall throughput. And then finally, bandwidth utilization. If I'm budgeting certain amount of the spectrum for it, I want to maximize how much of that spectrum gets used. So there are all these kind of goals that emerge that a good medium access control protocol will have. So variety of approaches exist within this framework now. So one approach is we can kind of do a very rigid time slotted approach. So we can think of time divided into time slots, and we can say in this time slot is your turn, in that time slot is some other transmitter's turn, and we can assign these slots. So this is called time division thing, and there is and this particular slide also talks in terms of non-time. There is also frequency. So I can assign fixed frequencies, I can assign fixed time, and everything is time slotted. So so we'll all have somehow clocks which are synchronized. We would basically agree upon the slot numbers, and we are going to do that. So that's one approach. The problem here is we need to be time synchronized, and we need to agree upon what those slots are. So that creates complexity. So the other approach which comes up is based upon demand. That is, we assign the chance to transmit when someone needs it. Okay, so that's kind of more efficient, hopefully. And there are a couple of ways to organize these things intuitively. So one is we do what is called as token passing. And kind of the idea is that I have a token, and when I have a token, I get to transmit. If I don't need it, I pass it to the next one. So imagine that all the nodes in the network, essentially we form kind of a ring out of them, and then the token passes through them. When the token reaches me, I get to transmit. Once I'm done, I pass the token on. If I don't have anything to transmit, I will move the token on. It does require that things behave fairly and all. There are problems with this. What if one entity sends a token to me, but I didn't hear the token? So now the token is lost. Or what if my radio crashed? All those kind of things come into play. So this thing, token passing, runs into some brittleness in this whole process. So much more common is the so-called contention-based approaches. Okay, these ones. And the way they work is the way kind of chaotic democracies work. We raise our hands, we kind of seek attention. So same thing out here, that we access the medium, we try to do something, and then we have the whole process be governed by some sort of etiquette, some sort of a norm, so that in case there is a collision, then we resolve it. So the idea is, if the channel is free, go ahead and transmit because no one was using it. If the channel is busy, then you follow an etiquette. And part of the question then is, how do you know that the channel is busy, right? So we follow something. So this we encounter every time in daily life also, right? I mean, you drive onto an intersection at the same time, and then we kind of all resolve with. In California, the rule is the person who came on the right has the right of way, right? So there are some ways of resolving this thing that emerge. So just to give you an example, Wi-Fi, which is not exactly a radio you would normally encounter in embedded devices because it's extremely power hungry, but you still find them, but it's not the best choice. So the way the MAC protocol in Wi-Fi is organized is that deep down it has this contention-based mechanism, DCF, which stands for Distributed Coordination Function. This is some jargon that they use, but this is the heart of the MAC protocol in 802.11. And then on top of it, they have built two ways for Wi-Fi equipped hosts or nodes to access this. One is they provide this contention-based service, namely you contend for the channel and you follow some sort of an etiquette, some sort of a protocol. But they also provide, less widely used, is what they call as PCF or point coordination function, which is contention-free, which is you get a guaranteed slot. So some nodes for certain kind of traffic, you can say every so often you are going to get guaranteed a turn to transmit. And as you might imagine, for traffic which is very predictable, very periodic, that may be a good thing to have, particularly for things like speech or video, which when the traffic starts, kind of a sustained traffic. For certain kind of sensor data, it might be the same story also. So this contention-free service is great for kind of periodic stuff. Okay, so they coexist. And before I let you go, I just want to show that how that core layer kind of works out, because it's the heart of this system. So the way it works is the following: when a source needs to transmit something, it is first going to examine the channel for a certain period of time, which is labeled as DIFS. IFS stands for interframe spacing. Okay. And they have several different kinds of interface spacing. This one is called DIFS. So the idea is that you're going to listen to the channel to see if anyone is transmitting. And so you basically go to your receiver, see if there is signal on the channel. If so, you will defer. If not, you will go ahead and transmit the data. And then what will happen is that you would see after this there are three different types of interframe spacing. So a couple of them are used for other purposes, which I'm going to later, but there was some other party, in this case, who would defer and would keep waiting until he sees the channel to be free for at least DIFS, and then he transmits. So this way, DIFS gets an indicator of spacing out the transmission. So in this case, what the other parties do is, so he would, let's say this other woke up somewhere out here, started seeing this transmission, so it will wait for the channel to be free for a certain time, and then it will wait for a certain amount of random time, so that this is part of their mitigation strategy, and then the data is transmitted. And the reason you do that is the following: if there are multiple others, you don't want all of them to start transmitting after seeing the channel free for DIFS. So you want to stagger them out. So they wait for DIFS for the channel to be free, and then they pick a random number in this window and wait for a certain amount of time. So you stagger them out. So this way you don't enter into, we all defer, we all transmit at the same time. There's a version out here where the receiver can send an ACK, but the receiver has to send an ACK within a short interframe spacing. So this SIFS is shorter than DIFS. so that if an ACK needs to be sent, receiver has to send very promptly, and this has to be done in a latency sensitive manner. So whatever software is doing it, it has a tight latency bound on it because these numbers are all in microseconds. So usually they get done in hardware or very tightly written software. So this is an example of how we are resolving contention between multiple transmitters which are sharing things, and we are doing it in time. There are very elaborate protocols and all, which, I mean, this is a very, very simplified view of a very complicated protocol, but this is how kind of things work. Okay, so I'll see you guys on Thursday, because Tuesday is going to be a discussion session. And be on the lookout if I see that I'll provide some alternative mechanism for uploading the zip files.
You don't have to worry though.